All right, time to take a look at another type of ionic compound. Really not much different from the last video, just a couple of little additional details. We're going to take a look at something called ternary ionic compounds. But before we do that, take a look at these formulas. I want you to look at these. If someone were to ask you, are these ionic compounds? Your answer should be yes. Even though they don't look like the compounds we've been working with, the key to understanding whether or not something is an ionic compound is, does it contain a metal? All of these contain a metal. Iron, magnesium, sodium, potassium, copper, barium, tin, and aluminum are all metals. These are all ionic compounds. Now, there is an exception to that, and we'll talk about it later, but for the most part, if you see a metal in a compound, it is an ionic compound. Because metals are losers, in order to become stable, they'll always lose electrons. They will become ions, and anytime an ion is in a compound, it's an ionic compound. Okay? So all of these are ionic. But they look a little different from the ones we've been doing. As a matter of fact, what's different about them is that they have more elements in them than the compounds we've been looking at. Look at this first one, FeSO4, has iron, sulfur, and oxygen. It has 3 elements in there. It looks different. It looks like there's going to be a lot more to do. Well, the good news is there isn't, because all of these compounds here contain something called a polyatomic ion. The word poly means many, atomic means atoms. Polyatomic ions contain more than one atom. As a matter of fact, we define a polyatomic ion as a tightly bound group of atoms that act as a unit and carry a charge. And notice that act as a unit is not only in bold, it's underlined. If I could make fireworks go off around it, I would, but I can't. Just understand that the act as a unit is very important, very important. Really, all a polyatomic ion, though, is it's a molecule that has a charge. That's all. It's a charged molecule. Most of them are anions, negatively charged. There are a few positively charged polyatomic ions. We'll see those as we go. There is a sheet that lists the ones that are most common. You don't have to be able to figure out the charge by looking at the periodic table or any of that nonsense. It's too difficult. So there's a sheet. It's on the website, on the files page. Download it, print it, bring it with you everywhere. Because anytime you need to write a formula, you'll be able to use it. And it's just easier than trying to figure out how to get the formula and the charge for them. You treat polyatomic ions exactly as if they were monatomic ions because they act as a unit. So even though it's made of more than one element, it pretends to be a single element. And it's treated like one. And that's what makes things a lot easier than you think they might be. The little wrinkle, the little addition is that when you have more than one of them in a compound, you have to surround the formula of that ion with parentheses. As you saw at the beginning of the video, if you rewind to that little list of elements of compounds, you'll see some of them have parentheses in there. And they do because there's more than one of the polyatomic ions in there. Okay? So what you saw at the beginning were what are called ternary ionic compounds. The word ternary means 3. And so those are compounds that contain 3 elements. But they're ionic compounds. They still just have one cation, positive ion, and one anion, negative ion. If the first thing you see is a metal, that's the cation. Everything else is the anion. And so the anions are usually polyatomic. At least one of the ions in a ternary compound has to be a polyatomic ion. Mostly it's the anions, but every now and then you'll get a positive one. You'll see an example of that in just a minute. You write formulas and name them exactly the same way as you do with binary ionic compounds. You write the formulas by balancing the charges. You name them by naming the 2 ions that are there. Nothing is new except when you have polyatomic ions and you have more than one of them, you've got to keep the formula written the way it is on the sheet. And that's why you need to use parentheses if you have more than one, so you don't change the way you write the formula. So let's do an example. We're going to write the formula for sodium sulfate. In order to write sodium sulfate, I need the 2 ion formulas. Sodium's easy. It's just Na. It has a +1 charge because it loses 1 electron to become just like neon. Sulfate, though, sulfate does not end in IDE. And because it doesn't end in IDE, it's not a monatomic ion. It ends in ATE. ATE means oxygen. So does ITE. Anytime you see ate and ite at the end of a name, it means there's oxygen involved. So since it's not monatomic, it's not on the periodic table, go to the sheet. You go to the sheet and you see that sulfate is written SO4 and it has a -2 charge. Sulfate must always be written SO4. It can never be written any other way. SO4 is the formula for sulfate. Okay, in order to write the compound's formula, I need to make sure that the positive charges balance the negative charges. They're not balanced right now. There's only one positive and two negatives. So I have to bring in another sodium, just like I did with binary compounds, so that I have a total of +2 charges over here, -2 charges there. Now I can write the formula. Na2SO4. That's sodium sulfate. All right, let's write the formula for copper 2 hydroxide. Notice there's a Roman numeral in parentheses in the middle of this name. That's good. That tells me which copper I'm working with. Copper is a transition metal. Transition metals often have more than one possible positive charge. Copper 2 tells me which one it is. It's copper with a +2 charge. So to write the formula for copper 2 hydroxide, copper is Cu, and I already know because it's copper 2 that it has a +2 charge. Hydroxide sounds like it might be monatomic because it ends in IDE. But the rest of the name, hydrox, that sounds like two different elements, hydrogen and oxygen, because that's what's in it. So hydroxide is written OH, and it has a -1 charge. It's always written OH. It's never written any other way when you have hydroxide in your name. Okay? So I've got two positive charges. I've got one negative charge from the hydroxide. I'm going to have another hydroxide in here in order to make the number of charges balance. Now there are two minus charges and two plus charges. Now I write the formula. One copper, Cu, but I have two hydroxides here. Now I can't write O2H2 because that's not hydroxide anymore. Hydroxide must always be written OH. So because there are two of them, I put them in parentheses. The OH goes in parentheses, and the 2 goes on the outside of the parentheses. CuOH2. That's how you write the formula for copper 2 hydroxide. All right, well, now let's try ammonium phosphate. Now this is a little trickier, but I want you to stop the video and see if you can do this one. I'll tell you this right now. Ammonium and phosphate are both polyatomic ions. They're both on that sheet. See if you can do it. Are you ready? All right, let's see how you did. This is how I'm going to do it. Ammonium ion, according to the sheet, NH4+. It's one of the unusual, rare, positively charged polyatomic ions. Interestingly enough, little side note, the name ammonium ends in the letters UM, which is what all metal names end in, UM. Either their original name or their current name ends in a UM. So copper used to be called cuprum, but aluminum, sodium, potassium, they're all end in UM. UM means it's a metal. Ammonium is not a metal. It's made of nitrogen and hydrogen, but it thinks it's a metal because it has a positive charge. Phosphate, 8 ending. ATE means it's not on the periodic table, it's on the sheet. PO4 with a -3 charge. Charges have to balance, but they don't. I have 3 negatives and 1 positive. That means I'm going to need a total of 3 ammonium ions. Each one with a +1 charge. That'll give me 3 positive charges to my 3 negatives. Now I can write the formula. Ammonium must always be written NH4. There are 3 of them, so I have to put NH4 in parentheses and put the 3 on the outside. There's only 1 phosphate written up there, so I put it here, PO4. NH4, 3, PO4. That's the formula for ammonium phosphate. Now that you know how to do that, I'm going to teach you a little shortcut. You have to understand how to write formulas before you can learn this shortcut. That's why I didn't teach it to you first. The shortcut is called the Criss-cross Rule, and it makes writing formulas a little bit easier. You still have to be able to figure out the symbol in charge of each ion. But in terms of writing down how many of each ion you have, you don't have to do any of that. Let's take as an example magnesium phosphite. Now, phosphite is different from phosphate. Take a look at the sheet and see if you can figure out the only difference between phosphate and phosphite. The difference is phosphite has 1 less oxygen, but they have the same charge. So magnesium, monatomic, Mg +2. It needs to lose 2 electrons to become like its nearest noble gas, neon. Phosphite, according to the sheet, PO3 -3. Here's how the crisscross method works. Instead of figuring out how to balance the charges, you take this 2 and you bring it down here. You take this 3 and you bring it down here. You write Mg with a 3. You bring the 2 down. Now, since 2 is bigger than 1, I have to put PO3 in parentheses, and I bring the 2 down on the outside. Mg3, PO3, 2. The very last thing I do is make sure that these two numbers that I just brought down and crisscrossed are in lowest terms to one another. 3 to 2 is in lowest terms. This is my formula. If they're not in lowest terms, you have to reduce it. Let's try this one. Tin 4 sulfate. Tin 4. Tin is Sn. The 4 tells me that it's plus 4. That's what the 4 means. Sulfate, we already saw, SO4 minus 2. Crisscross. Bring the 4 down here. Bring the 2 down here. Write SN2. SO4 in parentheses because I'm bringing down a number that's greater than 1, 4. Now that looks like it, but it isn't. And it isn't because 2 to 4 is not in lowest terms. It should be 1 to 2. So SN1, SO4, 2, that's the correct formula for tin 4 sulfate, lowest terms. If you don't believe me, deconstruct it, match up your charges, and see. You'll see that it works. Okay? So it takes practice, but you'll get it eventually.